ongoing story that we started years ago, back when I was still in Germany, before I moved to Austria. And as you can see from the list of people on the first slide, this is basically a collaboration between our institute here in Leoben, plus a lot of colleagues, more or less worldwide. And what I wanted to do is to show a little bit what you can do in terms of designing or creating new implant materials. I think I don't really have to motivate this, because we all know implant materials are more or less essential for an aging society. And there are, of course, a lot of materials around, but they're not really optimum for what you need. And so what I want to do is, in this little outline here, I want to give a little bit an overview about different possibilities you have for designing, especially titanium alloys. This goes all the way from classical, if you want to say so, metallurgy, for creating optimized alloy compositions, and then also including different processing routes like heavy mechanical deformation, or at the end of the talk, I want to give a brief outlook as far as it comes, for instance, to 3D printing technologies. So what is basically the driving force? The driving force is relatively simple. We all know that there are a lot of implant materials around, be it for knee fixations, be it for nails, be it for plates or whatever. The big problem is that they're usually not developed and not designed for really the application that you have in mind. So for instance, the classical titanium, aluminum, vanadium alloys come more or less from the aerospace industry. Stainless steels are around, cobalt chromium alloys are around, and so on. The problem is usually that these metallic alloys are much stiffer than human bone. Doesn't matter whether you talk about cortical bone, whether you talk about perhaps even osteoporotic patients. Nevertheless, these materials are way too stiff. The other problem is, of course, always the issue: are there elements in there like vanadium, like aluminum, that may raise some kind of allergies, or maybe at least treated with a certain caution? And of course, you always have to keep in mind that if you have a very strong metallic implant, then there is a kind of stress shielding effect. Basically, the load may be transferred through the implant, through the fixation, but not really through the bone. And this, at the end of the day, also deteriorates the bone tissue. And this is, of course, undesired. This is roughly sketched in the right-hand slide, where you simply have a look for instance, a classical deformation curve, a stress strain curve of a metallic material. And the blue curve, I think, shows pretty much at the first glance that whatever metallic material you use is typically much harder, much stronger, much stiffer than the bone you want to implant it. This is visualized here again in a certain simple way. This is an implant failure at the end of the day. So also fatigue issues play a certain role, toughness issues play a certain role. But the main essential part here is that the ratio of the stress divided by the Young's modulus, basically a kind of measure for the stiffness, is way too high for most of the metallic materials. So you want to look for something that has, on one end, of course, a high mechanical strength that you can transfer loads, but on the other hand, you want to have something with a relatively low Young's modulus. So you want to have a kind of elastic softening to prevent this. There are, of course, different kind of strategies you can follow, and this is not really new. This is done, I would say, since at least more than 20 years. You can, on one hand, if you look for the material side, of course, try to increase the mechanical stress the material can bear. This could be done, for instance, by classical alloy design. This can be done, for instance, by forging, etc. But this also can be done if you go in a direction of a little bit more exotic materials. For instance, you can talk about nanostructures, where you can increase the strength due to the very fine grain structure, or you can go all the way to amorphous structures, where you also typically have relatively high load capabilities. But of course, you have no classical dislocation activity, so you have different deformation mechanisms in this case. On the other hand, I said, you want to have a relatively low Young's modulus. Again, you can try to do this, and I show some alloy design attempts. for beta titanium alloys, you can do this by alloy composition adjustment, if you want to say so, or you can of course try to create porous structures that readily show right away that you may lower the stiffness of the material if you go into a kind of porous direction. So what we tried over the years was to go in different directions. One, as I already mentioned briefly, and I'll show some examples in a minute, is alloy design for beta titanium alloys, for BCC structured titanium alloys. The other way you can go is to go for severe plastic deformation techniques. There is a bunch of different routes. I just can briefly mention some of them. The idea there is not only to increase the strength by a grain refinement, but also to have a lot more grain boundaries, to have a lot more surface corrugations, perhaps compared to a coarse-grained material, which also may be beneficial in terms of an improved biocompatibility, an improved cell adhesion, or perhaps even improved cell proliferation. There are a lot of studies around over the years, different type of alloys, mostly focusing on titanium, different type of titanium grades, and this is also shown in the next transparencies. That's work done by Russian colleagues with severe plastic deformation called ECAP. This means equal channel angular pressing. So this is basically a heavy mechanical deformation. And what the left-hand figure shows is that you can indeed create nanostructured titanium, in this case commercially pure titanium, with a very high strength and still a decent ductility, which is by far better than for a variety of different other type of alloys. What this shows you is that even if you go for something like, call it pure titanium if you wish, there are applications that are already realized where you can go for implants, for stents, for screws, etc., etc. Nevertheless, the Young's modulus of titanium is beyond 100 gigapascal, so that's again still far beyond what you would like to have for bone. So one idea that we had was, okay, can we go for metastable beta titanium alloys? Beta titanium is basically the high temperature phase in the phase diagram that you can stabilize by a variety of different type of alloying elements, for instance molybdenum, for instance niobium, etc. And what you find is a composition dependence of Young's modulus. So if you just go to the right-hand side of this figure, this shows, okay, as a function of the so-called electron to atom ratio, you can decrease the Young's modulus values, at least compared to commercial alloys, to alpha alloys with a hexagonal structure. There are, of course, already some other phases that may come into the game. So it's kind of omega phase, or a martensitic alpha double prime phase with different crystal structures. And without going into the details, these additional phases are on one end desirable because they may increase the strength, but on the other hand, they typically induce embrittlement, which is of course not beneficial for implant materials. And on the other hand, they also increase Young's modulus. So what you would like to have is ideally something that is purely beta phase. And as this picture already suggests, you can do this in titanium niobium alloys, for instance, if you vary the composition ratio. Just to give you an idea how this looks like, and what you then typically do is you cast alloys, for instance, in our case, 10 millimeter diameter rods by a little bit special technique to keep the purity high. Tried this for different alloy compositions, and the X-ray diffraction patterns basically show you, okay, if you do it right for certain compositions, you may indeed get just this single phase beta type material. For other compositions, you may see, okay, there are again these orthorhombic phases coming into the game that you don't really want to have. On the right hand side, this is a little bit mixed or compared with this sketch that I already showed. The red dots here represent some of the alloys we tried and also show, okay, indeed, you can lower Young's modulus from something like 120 GPa for a hexagonal alpha type structure to roughly half the values, let's say something like 60 GPa, if you go for adjusted beta titanium alloy compositions. Nevertheless, the strength, shown in the upper right-hand diagram, the strength values are still sufficient to really have enough, call it mechanical load-bearing capacity for creating implants out of such materials. Of course, just casting is not enough. There are a lot of subtleties involved in the whole procedure that determine what kind of microstructure you get, what kind of grain size you get, etc., etc. And to make a long story short, I just wanted to show you this kind of sketch here. You can, for instance, do an annealing treatment. You can do an extra cold rolling. You can do an extra recrystallization, for instance, not just in a single step, but in multiple steps to simply tune the microstructure to a certain grain size, to a certain orientation that you want to have, and that may be beneficial for the implant. So altogether, in terms of a kind of engineering perspective, it's not just enough to create the right material, but you also have to get the microstructure right. And this is something you can do by thermomechanical treatment. Again, just a comparison. What happens then if you do this? For instance, these EBSD maps show you a little bit how you can tune in the grain size in terms of a relatively coarse grained, in terms of a relatively fine grained material. And it also shows you that due to the processing, if you roll, for instance, something, there may be a certain anisotropy in the material that you may exploit if you really can apply it in a certain direction, or that you want to avoid and have a really equiax microstructure for a more globalized application where you don't really know how the load is directly transferred or the load direction is really applied. And this, of course, whatever you do, tunes in again the deformation curves. So you can tune in from a relatively hard, but still relatively, not really brittle, but not really too ductile material, all the way to a softer material with a lot of work hardening, like the orange curve here shows, with a lot of load bearing capacity and a large tensile deformability. So this is one thing you can do with casting and with rolling. You can also do it the other way. You can do it like the Russian colleagues usually try to do it, with a little bit more brutal deformation techniques, meaning methods that rely to severe plastic deformation. So for instance, like shown in the middle part here, you either take a rod and more or less, if you want to say so, extrude it around a 90-degree angle, or you do something like high pressure torsion on the right hand side, where you have a little plate that is put into a two, or in between two anvils, where you apply a large pressure, and you basically also have a torsion deformation in there. Or you do a successive rolling procedure like we've shown in the middle part, abbreviated by this phrase ARB, which means accumulated roll bond. So there are different mechanical deformation methods. The reason to apply this is because these methods allow you to gain even a more refined microstructure. And we tried this again for titanium niobium alloys. And again, the X-ray diffraction patterns basically tell you if you do this right with a certain deformation temperature at a certain number of passes, for instance, because you have to do this in a repeated fashion, you can get single phase beta type alloys with a very, very fine microstructure, which have very high strength values. So you can exceed something like 1000 MPa, for instance, with a large ductility. Of course, this means, again, you have to look very much in detail. At the end of the day, what are really the deformation mechanisms? Are they the same like in coarse-grained material, etc., etc.? But this would be a separate talk by itself. But at the end of the day, what you can do, if you just check the hardness, for instance, if you check Young's modulus, you can get very fine microstructures, which are very hard, very strong, through these different techniques, with, again, Young's modulus values, which are mostly defined by the alloy composition of, let's say, around 60 GPa. So similar like I showed it at the very beginning for this casting and annealing procedure. But the strength values are high. One specialty that we have in-house is the so-called high-pressure torsion. Like I said, You have two anvils, a little disc button shape sample in between. You apply the pressure. You have a torsion deformation. You get very fine grain sizes. And this was something that we tried for small scale implants, not for big hip replacement parts or something like that, but for relatively small scale parts. And what you hopefully can see is you can get extremely fine microstructures on the order of several nanometers, which have a relatively homogeneous overall appearance. On the other end, depending on the position of such a disc, this is shown here on the right-hand side, you have a certain hardness variation because there is basically a stress and a strain gradient across the disc. So for instance, if you do it carefully and take samples at different positions under different directions, you will find different variations in hardness or in strain. So the trick here is to adjust the processing in such a way that you get the optimum structure, or a structure with a certain stress strain gradient if you want, in a direction that you want to have, for instance, at the end of the day in your implant. So it's not just that the composition is, let's say, fixed, but you can adjust locally the microstructure and the properties. This is shown here again for looking for such HPT specimens in different directions, be it an axial direction, the shear direction, or the as-cast initial direction, and you can easily see how strongly the deformation curves vary between these different orientations. So you can, depending on the deformation characteristics, basically again tune in the mechanical response in a certain way that you can have and can use this distinct orientation dependence of the mechanical properties for specific purposes. This is basically all now, or was all, about casting severe plastic deformation. You can also, of course, go the other way around. You can start and say, okay, why not simply using powders? Powder metallurgy is in that sense nice because it usually allows you to create, again, metastable phases. And again, such alloys like titanium, niobium are usually metastable alloys. So basically, this is one idea behind the story, that you get the phase more or less relatively easily through a solid state melting procedure, avoiding any melting. On the other hand, powder metallurgy is always a little bit a dirty procedure, so you also have to take care of contaminations. So you have to do this again under relatively clean environments. Nevertheless, what you can get are basically metastable beta titanium alloy powders. Typically, and you have to believe this for the minute, with a refined microstructure, because also milling is a kind of severe plastic deformation that refines the grains, with a relatively high strength. And that's the other idea behind the story. Since you have powders, you can relatively easily, of course, try to go in the direction of porous materials or porous implants. Again, just a little overview to give you a glimpse or an idea how the phases may change, or how the microstructure may change if you take these powders and do, for instance, different consolidation treatments, because at the end of the day, you want to have an implant, so you somehow have to consolidate the powders. You can do this, for instance, if you start from the powder, and HP stands for high temperature pressing or hot pressing, or you can do this by spark plasma sintering. So you can use different consolidation techniques to get the implants at the end. And of course, this all means that whatever heat exposure you have, whatever pressures you have, there may be subtle changes in the actual microstructure. There may be subtle changes in the actual phases that you have at the end of this consolidation. And of course, this all means that the mechanical characteristics are again different. And what you can easily see here, hopefully, in again this comparison of deformation curves on the left-hand side, is that depending whether you do this by spark plasma sintering, whether you do this by high or hot pressing, high temperature pressing or hot pressing, you may get again very different mechanical properties or different mechanical strength levels. Nevertheless, all these different variants here would still be suitable for creating implants out of this. And then, of course, the next step is, can we do this and create porous structures? One way of doing this is adjusting, for instance, the sintering parameters and avoid getting a fully dense part at the end by simply adjusting the sintering parameters. The other way would be, for instance, to add some space holder, for instance, sodium chloride, to these powder particles, mix the whole thing, and then consolidate it. And before, perhaps, or during the sintering, you may leach out this sodium chloride, and this gives you then some kind of porous structure, like it's shown on the lower left-hand side. And this, of course, means that besides having the face right with intrinsic mechanical properties, you can adjust Young's modulus or the stiffness through different levels of porosity. Nevertheless, this is just shown on the upper slide or part of the slide here. Even if you do this for porous materials with, in this case, 30% porosity, you still maintain mechanical properties that are sufficient for creating implants out of this. So powder metallurgy is an alternative route. And if you have powders, either through a solid state reaction or through a kind of gas atomization, for instance, then of course you can also do additive manufacturing, like Jen showed it nicely for different type of alloys in his talk, going in a totally different direction. But of course you can use the powders and create different kind of scaffold structures with different geometries, different level of porosity, etc., etc. And this, of course, adds another variant or another parameter, if you wish, to the overall mechanical performance. So there are plenty of possibilities, and I simply don't have the time to go into the details, but adjusting the porosity, adjusting, call it the lattice structure, if you wish so, can in fact really tune in the properties very close to the desired performance you want to have for a specific patient. And since this is a relatively fast technique, this would be something like a kind of, if you know the parameter setting for a given alloy, for really adjusting implants on a personalized basis. Two comments along this line, because this would again be a separate talk. Of course, it's not that easy to just print the materials with a certain geometry, for instance, with a certain scaffold structure. But then this additive manufacturing is usually something that melts the powder particles. So it very much depends on the relative energy density that you put into the material during this melting procedure and the laser scan speed. And this can create, of course, parts always for the same given alloy with a totally different relative density of the part, with different mechanical performance, etc. So this is nowadays, I would say, something that is followed worldwide by a variety of different groups. And this is just basically, call it a kind of summary slide that should give you the idea that A, if you look for the mechanical properties of different type of alloys here, you can create implant materials with the desired mechanical properties, to make a long story short. How to do this, especially for a given set of processing parameters, is a little bit tedious work, but it's doable, it's possible. And the lower left-hand figure, or two figures, simply show you again that it very much, if you do additive manufacturing, it very much depends on the laser power that you couple in, on the scanning speed, because this all affects the phase formation, this all affects the porosity, this all affects what kind of anisotropy or not you may have in your built part, including variations or possible variations of the hatch style, of the scan strategy that you may use. All these kind of schematics simply indicate, okay, the arrows are basically the way the laser runs. You can do this in a variety of different hatch styles. And this gives you a wealth of possibilities how to really tune in the properties. So this brings me to the summary. I hope I could show you in this presentation that there are, from the, call it metallurgy side, a lot of fascinating possibilities for really tuning in and creating, call it advanced implant materials, if you want to say so. The This is doable by different techniques, be it through casting, through rolling, through deformation, through additive manufacturing, and so on. And at the end of the day, this is a possibility to really create personalized implant materials. What I totally neglected here in this talk is how you may, for instance, functionalize surfaces, whether you can add in a porous structure something like, call it drug delivery or drug release substances, etc., etc. But I think this is a way that you can really go for, and that has quite some promise in the next years. Of course, this is only a summary of ongoing work where we have a lot of collaborations with a lot of different people, basically in Austria, in Germany, more or less worldwide, and there is also a lot of support for this work through different funding agencies. So thank you very much for listening, and I hope I could give you a little bit an overview of what is possible in this area. Thank you very much.